Hello and welcome back to Chapter 3. Today we're going to look at 3.4, which deals with exponential and log equations. Now so far in Chapter 3 we've looked at definitions, graphing, and different properties of exponential and log functions. Now there's two key strategies that we're going to use in Section 3.4, which is where we're going to be solving exponential and log equations. Those key strategies are going to come from our one-to-one property, which says if a to the x equals a to the y, then we know that x has to equal y, or if log base a of x equals log base a of y, then x also must equal y. Or we have our inverse property, and our inverse property says that a to the power of log base a of x equals x, or log base a of a to the x equals x. These two properties are critical in solving exponential and log equations. So if you don't know them, please make sure to write them down in your notes, and please make sure that you do memorize them. So to start out with, we're going to look at example 1, which says 2 to the x equals 512. Well, in order to solve for x, we have to rewrite this problem. So I have 2 to the x equals 2 to what power up here? Well, that power up there is the 9th. So I really have x then equals 9. Likewise, for part B, we have the natural log of 5 minus the natural log of x equals 0. Well, if I rewrite this as the natural log of 5 equals the natural log of x, both of these have a natural log in them. So I can assume then that 5 is equal to x based on the one-to-one property. For part C, I have 1/5 to the power of x equals 125. I can rewrite this 1/5 as 5 to the negative x. And I can rewrite 125 as 5 to the third. So now this is going to give me negative x equals 3, or x equals a negative 3. And if I go on to D, I can actually use my inverse property because I have e to the x equals 13. Well, this one's a little more complicated to solve, but I know that I can cancel out that e with a natural log. So if I take the natural log of e to the x, and I take the natural log of 13, my natural log and e are going to cancel out, and I'm going to be left with x equals the natural log of 13. And I can use a similar concept in part E, where I have the natural log of x equals a negative 8. Well, if I take this and I go e to the natural log of x equals e to the negative 8, again, my e and natural logs are going to cancel out, and I'm going to be left with x equals e to the negative 8th. And for part F, I have the log base 10 of x equals a negative 2. Well, remember from your inverse property, the only thing that can cancel out a log base 10 is if I have 10 to some power of a log base 10. So in this case, I'm going to go 10 to the log base 10 of x equals 10 to the negative 2nd. So my 10 to the log base 10 are going to cancel, and I'm going to be left with x is equal to 10 to the negative 2nd, which is really equal to 1 divided by 100. So we do have a couple strategies here for solving exponential or log equations. The first thing you need to do is you need to rewrite your original equation in the form of a one-to-one property. Then, if you have an exponential equation, you want to put it in log form and apply your inverse properties. If you have a log equation, rewrite it in exponential form and apply the inverse properties. So we have a few examples that's going to be dealing with these strategies here. So for example 2, part A, it says e to the negative x squared equals e to the 5x plus 6. This is already written in the one-to-one form, so all I have to do now is look at my exponents here And here, use a one-to-one property and set them equal to each other. So I have a negative x squared equals 5x plus 6. So if I move my negative x squared over to the other side, I have x squared plus 5x plus 6 equals 0. Well, from there I can factor, and I have x plus 2 times x plus 3 equals 0, which then tells me that x equals a negative 2 or a negative 3. You really should plug these back in to your original equation, make sure that they work, because sometimes with these you can still get the extraneous solutions. And if you remember, an extraneous solution is something that works out algebraically but will not work out if you plug it back into the original equation. Now in this case, both of these do actually work. Now for part B, let's look at that. I have 4 times 3 to the x equals 64. I'm going to go ahead and divide both sides by 4. So then I have 3 to the x equals 16. And remember, we can cancel out that 3 to the x by taking the log of base 3. So I can really rewrite this as log base 3 of 3 to the x equals log base 3 of 16. And if I simplify that now, log base 3 of 3 is going to cancel out and leave us with x equals the log base 3 of 16. And I'm so thankful I learned the change of base formula. So now I can actually simplify that and say that x is equal to the log of 16 divided by log base 10 of 3. And the decimal approximation of that then is going to be about 2.524. Now example 3 says to solve, and we have 5 minus 3 to the 3e to the x equals 2. Well, the first thing we're going to do is we're going to, actually just to keep the e stuff positive, I'm really going to add 3e to the x to both sides and subtract 2 from both sides. So what that gives us then is 3 equals 3e to the x. Then I'm going to divide everything by 3, and we have e to the x equals 1. And in order to get rid of that e, I know that I can take the natural log of both sides. So the natural log of e is going to cancel, and we'll be left with x equals the natural log of 1. And the natural log of 1 really is x equals 0. Example 4 says to solve 6 times 2 to the t plus 5 plus 4 equals 11. So we're going to have to kind of undo our order of operations, and we're going to subtract 4 from both sides. This is going to give us 6 times a quantity of 2 to the t plus 5 is equal to 7. I'm going to divide by 6, so I have 2 to the t plus 5 is equal to 7/6. And now I need to get rid of that base 2. In order to get rid of a base 2, I'm going to take the log of base 2 of 2 to the t plus 5. And I have to do that on both sides. So log base 2 of 7/6. My log base 2 of 2's are going to cancel. So I have t plus 5 is equal to the log base 2 of 7/6. And if I get rid of that 5 right here, I really have t is equal to a negative 5 plus the log of base 2 of 7/6. And you can actually approximate that by doing your change of base on this piece here and then adding a negative 5 to it. And if you do that, I got something around a negative 4.778. Now example 5 is a little bit tricky, but it is kind of fun. Example 5 wants us to solve e to the 2x minus 7e to the x plus 12 equals 0. The one thing that this example relies that you know is that e to the 2x is really equal to e to the x, and that's being squared. So if you think about it like that, we really have e to the x being squared minus 7e to the x plus 12, and this equals 0. You'll see that this right here is really a quadratic formula. So we can actually factor that. So I'm going to have an e to the x and an e to the x. Factors of 12, because I have a positive 12 here, they either both have to be negative or they both have to be positive. Because of that negative 7, I know that they're both negative. And factors of 12 that will add up to a negative 7 are going to be a negative 3 and a negative 4. So now that I have this factored, I can take each factor, set it equal to 0, so I have e to the x minus 3, set it equal to 0, and I have e to the x minus 4, set it equal to 0, and now I can solve both of these. So I end up with e to the x equals 3. To cancel out that e, I'm going to take the natural log of both sides. So I end up with x equals the natural log of 3 as one of my solutions. And if I do the same thing on the other side, I have e to the x equals 4. We'll take the natural log of both sides. Those are going to cancel, and we're going to be left with x equals the natural log of 4 then. So these would be your two solutions. Now we've already done this a little bit, but just as a reminder, in order for us to solve log equations, we need to rewrite them in exponential form. And this is what we call exponentiating. So for example 6, we have the natural log of x equals 2/3. Well, remember, in order to cancel out a natural log, we have to exponentiate it or rewrite it as e to the natural log of x, which equals e to the 2/3. Well, your e and natural log are going to cancel out, and that's going to give you x equals e to the 2/3 power. And e to the 2/3 power is approximately equal to 1.948. For part B, I have log base 4 of 3x plus 2 equals log base 4 of 6 minus x. In order to cancel out a log base 4, I have to exponentiate, or say 4 to the power of log base 4 of some stuff equals 4 to the power of log base 4 of some more stuff. Now when that happens, my 4's and log base 4's are going to cancel, and we're left with the 3x plus 2 equals 6 minus x. Now all I have to do is I have to solve for x. So when I do that, if I add x to both sides, I get 4x equals, and I'm going to subtract 2, 4, or in this case, x equals 1. Similar to part B, we have part C. Part C, we have log base 3's and everything. Now the only difference with part C versus B is we do have a subtraction of logs of the same base. So I can really rewrite that as the log base 3 of 5x plus 13 divided by 6 equals the log base 3 of 3x. And you can either exponentiate here, or you can use your one-to-one property. Because both of these have the same log values, I know that these here have to be the same. So I can rewrite that as 5x plus 13 divided by 6 is really equal to 3x. I want to clear out my denominator, so I'm going to multiply both sides by 6. When I do that, we get 5x plus 13 equals 18x. When I subtract 5x, I have 13 equals 13x, or x equals 1. Example 7 wants us to solve 3 times the log base 4 of 6x equals 9. Now you could take this 3 and put it up here on the x cubed. However, it's not going to benefit us as much as if I were to go ahead and get rid of it right from the get-go and divide everything by 3. And what that does is that gives me the log base 4 of 6x is equal to 9 divided by 3 is 3. Now if I exponentiate both sides, I end up with 4 to the log base 4 of 6x equals 4 to the third. Log base, or 4 to the log base 4 of 6x is going to give me 6x, and 4 to the third is equal to 64. And if I solve for x, I end up with 64/6. And if we reduce that down, that gives us 32/3. And as I mentioned earlier, one thing we need to be careful of is we need to be careful of extraneous solutions. If you take this solution here, plug it in up here, you'll see that it does work. So let's go ahead and look at part B. Part B says that we have log of x plus the log of x minus 9 equals 1. Well, we can go ahead and rewrite this as 1 log by condensing. So I really have the log of x times the quantity of x minus 9 equals 1. So if I exponentiate everything, and I'm going to say 10 to the log base 10 equals 10 to the first, 10 to the log base 10s are going to cancel, and I'm going to be left with x squared minus 9x, and all I did was distribute that x, equals 10 to the first, or 10. So I can rewrite that as x squared minus 9x minus 10 equals 0. And if I solve that, I see we can factor, and this is going to give us x minus 10 times x plus 1 equals 0, or x equals 10 and negative 1. Now I can plug a 10 in for either one of these because log of 10 will give me a number, and 10 minus 9 is a number greater than 0, so I can take the log of a number greater than 0. However, if I go to plug in a negative 1 into this equation here, I cannot take the log of a negative number. Therefore, my only true solution is x equals 10. X equals negative 1 is an extraneous solution, so we do not count it. And the last example we're going to end on is a story problem. It says you deposit $500 at 6 3/4% interest that's compounded continuously. How long is it going to take to double your investment? Well, remember, when we're compounding interest continuously, we're going to use the per equation. So to start out with, let's plug in everything we know. We know that we want to, our A value is going to be doubled what we deposit initially. So to double our initial deposit, my initial deposit was $500. So I know then A is equal to 1,000. P, which is my initial investment of $500. I have E. My R value is going to be my interest rate as a decimal, which is 0.0675. And I don't know my T value. That's actually what I'm trying to solve for. So I'm going to go about getting the E piece by itself. So I'm going to divide by 500, and 1,000 divided by 500 is 2. So 2 is equal to E to the 0.0675 5t. Now I need to go ahead and get rid of this e, and to do that I need to take the natural log of both sides, which is then going to cancel that out. So then I'm left with a natural log of 2 is equal to 0.0675t. And then if I go ahead and solve for t is going to equal the natural log of 2 divided by 0.0675. And if you type that in, then t is going to be approximately equal to 10.3 years. So a little over 10 years, I'm going to be able to double my investment of $500 if I'm compounding my interest continuously. And just like in the last video, I'm going to come around and check. I want you to give these 3 problems here your best effort, and we'll see where we go from there. And I do apologize that for number 3, this here should be an e. So it should be 3 to the ex, or 3 times e to the x. On that note, I hope you have a great night, and we will see you in class tomorrow.